And we have another problem that is called something oscillation of a plate over a half cylinder. And the problem statement is a thin plate of length L, you can see here, rests on a half cylinder of radius R. Derive an expression for the period of a small oscillation of the plate. That's right. That's right. You know where the friction is. Here it is, because it is rotating about on fixed axis, and here it must be. And I have drawn a picture like this. This is basically the cylinder that you can see in the picture, and this is the equilibrium position of the plate, and its center of mass lies here. Definitely, then only can the equilibrium condition can be achieved. And in this condition, this center of mass has shifted to some position here. The angle is small, of course this angle is small, and this is not let's solve it. Let's play a game. This is the equilibrium position, and this is the extreme position, one of the extreme positions, so that this angle is not simply theta but theta max. Of course it is theta max, I am writing as theta m, and this is the extreme position, position 1, call it position 1, and call it position 2, the equilibrium position, call it position 2, and theta m is the angular amplitude. And so it has come to, it has lost some distance like this, some distance. And if the radius of the sphere is equal to r, then this length is going to be r, and the whole length is r, and this length is going to be r cos theta m. So the lost height by the rod in the process is going to be h equals r minus r cos theta m. That means r into 1 minus cos theta m. And of course this theta m is very small, but you can see if I put theta m equal to 0, then cos 0 is going to become 1, and this height will be equal to 0. So the height is not 0 definitely. So remember the expansion of cos x, and you will get something, the second term, as you know what to write here, and so that this h thing will become simply as approximately as r theta m square by 2. Yeah. And if you know the expansion of sine theta, then you can also write it. So this is the thing here, because you can't go for 0 simply, that it doesn't changes anything. And now you can write the conservation of energy thing. So make the preparation in the position 1, that is one of the extreme position. Here, if this position is extreme, its kinetic energy is going to be 0. Position 1, kinetic energy is going to be 0, and its potential energy is simply minus mgh, and it is minus mg, and h is r theta m square by 2. So these are the values of kinetic energy and potential energy equal to 0, and in writing this potential energy I have taken the position of datum here. That means here is the gravitational potential energy of this plate is equal to 0. And now in position 2, when we talk about position 2, position 2 is the equilibrium position, that means this position here. So it will have a kinetic energy, maximum kinetic energy, and its potential energy is of course equal to 0. So in this position 2, potential energy is equal to 0, and kinetic energy here is half I, the moment of inertia of the rod about its axis of rotation perpendicular to its length. So this will be ml square by 12, nothing else, half I. Its angular velocity here, I don't know what, but I would like its angular velocity as omega. So it's angular velocity here, angular velocity of the rod, not the angular frequency of oscillation. The angular velocity of the rod is omega here, half I omega square. So I'm going to write next half I equals 1 by 12 ml square and omega square. The angular velocity of the rod at its equilibrium position. And if you can remember one of the formulas between velocity of a particle oscillating around an equilibrium position being a distance x from equilibrium position, here are the amplitudes. These two are extreme positions. So at this point the formula for velocity is simply written as v equals omega under root a square minus x square. You have remembered it several times, you forget it usually, but you know. So at the extreme position x is equal to 0, so at extreme position velocity is omega. This is also a memorable choice. Most often people remember it. The velocity at the equilibrium position is omega. Here this omega is the angular frequency of oscillation. You can confuse between both omega. First I wrote omega as angular velocity of the rod, and this omega is different. This is the frequency, angular frequency of natural oscillations. Natural frequency of oscillation, sorry. So I have written it in the symbol omega n. These two omega are different. So this is related to oscillation, and that was related to the angular velocity of the rod. So if you can try to write in terms of angular velocities, this v you can write r d theta by dt. Theta is changing, so you can the radius was of course a small r, not capital R. So you can write v equals r omega, that was r d theta by dt, equal to angular frequency of natural frequency of angular oscillation, and a is of course the amplitude, that in our case is theta m. R theta m is the amplitude of oscillation here. So both r can be cancelled out, and you can write here d theta by dt, that is in case our omega equals omega n, the natural frequency of oscillation multiplied by theta m. And now you can write something like here, that your kinetic energy was half 1 by 12 ml square at half I. Omega is here, so you can write is omega, the natural frequency of oscillation, omega square, theta m angular amplitude square. And you can compare things like potential energy. You can write the condition for you can write the equations of equation for conservation of mechanical energy, that is kinetic energy as potential energy at position 1 equal to potential energy plus kinetic energy at potential 2. And initially there was potential energy, and its value was simply mgr something, what, though it was with a minus sign, but I don't need it. So what was the mgr theta m square by 2. So this is theta m square by 2 plus kinetic energy was 0 here, and potential energy was 0 at this position. They are relative things, and kinetic energy is 1 upon 24 ml square omega n square theta m square. And you can do one thing, you can just cancel them out, and you will get, I think, many other things will get cancelled. Not many things, but so you will get the angular frequency for natural frequency for angular oscillation, and that is going to be 12 gr upon l square. So the time period is 2 pi by natural frequency of oscillation, and that will become 2 pi under root, what is it, l square upon 12 gr. Okay, so I guess this is the answer. Thank you very much for watching.